In this video, we're going to look at proposition 5.3.2 about volumes using double integrals. So if S is a region of R3, meaning a solid, bounded below by a function z is f1 of xy, and bounded above by a function z is equal to f2 of xy over a region D in the xy plane, then the volume of S is, V of S is the double integral over D of the top surface, f2 of xy, minus the bottom surface, f1 of xy, dA. Top surface minus bottom surface. And you might notice that this is the analogous formula to the formula for the area of a planar region using a single integral, where you did top curve minus bottom curve between two bounds. We're not going to prove this proposition, but instead we're going to look at the following geometric rationale for the volume of a solid using double integrals. So imagine that we had a top bounded surface. So here's our surface f2 of xy, and we had a bottom boundary, which let's call this guy f1 of xy, like in the proposition. So we're talking about the volume captured between those two surfaces over some shadow region D down in the xy plane, right? So those guys are floating above some region D. Now, the insight is the double integral we know is interpreted as volume. So if we take the double integral of just f2, so let's grab f2 here. If we take just f2, so something like this, over our same region D, well, we've got the same bit of solid area that we had before, but then we have it all the way down to region D as well, right? That's the interpretation of the double integral as volume under a surface. But we don't want all of this area or all of this volume. We want the volume just between those two bounded surfaces. So we're going to take the first volume and subtract off the volume that's under the bottom surface, right? If we subtract off the volume that's under here, so we take all of this and we subtract off this, then what are we left with? The bit in the middle, which is that. So that's sort of the geometric rationale for why the double integral of the difference of two functions, the top minus the bottom, gives us the volume of the solid region in space that's trapped between them. In the next video, we'll do example 5.3.2, where we'll use this proposition to calculate the volume of an actual solid.